again, welcome to the Academy. This is part of a video series on calculus 3 topics, and this time we'll be talking about surface integrals. So previously I talked a little bit about them, but not in much detail. Basically, just like a double integral integrates over a two-dimensional region in the xy plane, a surface integral integrates over some surface like this. And basically, it integrates a function, so there's a surface S. This is the integral of x, y, z ds, or ds, you can imagine taking slices delta s, and then as the slices get smaller and smaller, it becomes ds, and you add them all together. But there's also an alternate type of surface integral for vector fields. So you have a vector field F, and this is for flux. So if F represents some fluid, for example, and you want to see how much flow there is through a surface, here's the surface S again. And so F is your vector field. The flux is how much the field F crosses through the surface. And so what you want to do is at each point on the surface you integrate the vector dot product with a normal vector F dot n, where n is normal to the surface. And this tells you how much F is in the direction of n. Basically, this is normal, how much F is going perpendicular to the surface, how much is crossing through the surface as opposed to going along with the surface. And then when you integrate this at every point on the surface, so you integrate F dot n ds. It's also written as F dot ds, where ds is just a short form of n ds. And this is the flux through the surface. And so now we want to see how to calculate ds. Basically, the way to do it is you want to parametrize the surface. So if we point on the surface, if we have a coordinate system, so we have a position vector r, and since it's a two-dimensional surface, it needs to have two variables, r of u and v. And of course, r is just x, y, z, the position vector, where x, y, and z are all functions of u and v. So basically, the way to do this is you want to see how r changes as u and v change. So we want to see if you have v constant and change u a little bit. Let's say it changes like this. So you have your displacement vector delta r with u, and then if you hold v constant and change u, you have another displacement vector delta r with respect to v. And basically, we see this sort of creates a parallelogram, and redraw it bigger. This is delta r u, delta r v, and the area here is delta s. So if we want to find the area of a parallelogram, well, we know that the area of a parallelogram in general, we have vector A and B. Is the base B times the height. If this is the angle, the height would just be A sine of the angle, A sine theta, which, as we know, is also the cross product of A and B. The magnitude of the cross product is A, B sine theta. These are the magnitudes of these vectors. And so in this case, we have delta S is approximated by delta RU cross product delta RV. Now if we wanted, instead of delta S and delta S, to find this form for the vectors, it's actually also pretty easy, because the cross product is already normal to the two vectors, and the magnitude, of course, is still the same. But this is actually just the cross product itself. So it will get infinitely smaller and smaller. We have n ds equal to, well, the change in r with respect to u is just the partial derivative of r with respect to u. Cross product with a partial derivative with respect to v. This is in general how you find n ds, and of course ds is just the magnitude of ds is the same thing as ds, d vector s. So that would just be the magnitude of the cross product. So let me do an example. Or I guess a special case. So let's say we already know our surface is a function z equals f of x comma y. Something like x squared plus y squared. That would look like this. And so in this case, when we have r of u and v, we can just use x and y. And z is f of x. So u, v, and f of u and v. And so ds n ds, which is the same thing as d vector s, is, well, it should be the cross product of the partial derivative of r with respect to u. So, well, the partial derivative of r with respect to u is, well, this is, let's see, 1, this would be 0, that would be partial f with respect to u, whereas the v is a similar thing, it would be 0, 1, partial f, partial v. So we want the cross product of these two. Cross product would be 1, 0. Partial f with respect to u, 0, 1. So I, 0, j, 0, k is 1 minus 0k f partial u I plus partial f partial v j, or negative partial f partial u negative partial f partial v 1. But of course, u and v are just x and y. So this is negative partial derivative with respect to x, the negative partial derivative with respect to y, and 1. And if we want to know ds by itself, that would be just the magnitude of this, which is the square root of the sum of all of these squared. So that's 1 squared is 1 plus partial of f with respect to x squared plus the partial of f with respect to y squared. Now, of course, all of these, I want to mention, are going to be with respect to the variables. So this is dx dy. So this would be, this is du dv. So this is transforms the integral from ds, which is the surface, to the flat surface or flat region in the uv plane, or in this case, uv is just x and y, in the xy plane. So you would look at the boundaries, and you would see how x and y change, and you would find the region R, and you would integrate dA, which is dx dy or dy dx, depending on the situation. So in this case, if we have it be x squared plus y squared, the surface, and say it's just the unit circle, which goes from 0 to 1, that would just be, so ds, this is for f equals x squared plus y squared. We have ds equaling, well, this negative partial with respect to x, that's negative 2x. Then with respect to y, negative 2y, 1, or if we just wanted ds by itself, that would be 1 plus square root of 1 plus 4x squared plus 4y squared. Or these are dA or dx dy. And so that's how you transform integral ds into just an integral. So this would become an integral r over the region R, and ds would become this, and it would be dx dy. It would be an ordinary double integral. And now, just to clarify, if there's a function here, say g of x, y, z, this function has nothing to do with this function over here. This function is just a function that describes the surface S. So this is all part of the S. So what you're doing, when you're integrating, you're either going to integrate another function, and ds will become this dx dy, and then you would integrate that. But x, y, z, you would substitute x, y, and then the surface. So z would become the surface, f of x become y, because z is constrained. Or in the general case, when you have u and v, x, y, and z will all be substituted as functions of u and v, because that's what they are here. So in R is just x, y, z, where x is a function of u and v, so is y, and so is z. And you would have du, dv. So everything would be in terms of u and v in that case. In this case, where you just have u equals x and v equals y, everything is in terms of x and y instead of u and v. So that's basically how you would do surface integrals. Thanks for watching, and I'll see you in the next video.